Good morning, ladies and gentlemen, professors, and all the attenders. My name is Qianyue Qu, a PhD student from Innovation Academy for Precision Measurement Science and Technology in Wuhan, China. And it is an honor to share my work, but I'm sorry I couldn't make it to the talk on site due to visa reasons. So I had to talk by recording this video. The title of my talk is a preliminary study of ultra-wide range shuttled NMR relaxometry based on compact atomic magnetometer array. And as this part of the work is still in progress, I will primarily share a series of recent advancements made. This talk will be these fellow 4 parts. First, I will describe the background of relaxometry, and then I will introduce our ultra-wide range shuttle NMR relaxometry, and followed by our preliminary results using water and the contrast agent, and finally is our outlook. First is a background about this topic. NMR ionization is a process by which an excited magnetic state returns to its equilibrium distribution. There are 2 mechanisms involved, spin lattice and spin-spin. Spin-spin ionization is also referred to as a transverse ionization, or T2, and it describes the decay of the excited magnetization perpendicular to the applied magnetic field. And spin lattice ionization is also referred to as longitudinal ionization, or T1, and it describes the return to equilibrium in the direction of the magnetic field. And look at that picture. T1 ionization is correlated with magnetic field strength, which is a reflection of various interactions. So here we primarily study the T1 ionization. In the case of T1, the measurements may be carried out using evolution time under a particular magnetic field. We often use the field cycling NMR method to get a variation of the longitudinal ionization rate when the intensity of the applied magnetic field is repeatedly changed among different values. The figure below shows a common field cycling NMR measurement sequence. The sample is measured under another magnetic field after passing through a variable ionization field, and depending on the presence or absence of polarized magnetic field, it can be divided into a prepolarized and a non-polarized sequence. And then we can get a recovery curve or decay curve, and we can fit it and get the T1 of the sample. The measurements of T1 have been studied and applied very extensively, such as monitoring the pore size in geotechnic, and analyze the oil component in photoscience, or design the contrast agent in MRI. After more than 2 decades of development, many techniques have been proposed for field cycling ionization measurement. On the left is a commercial fast field cycling ionization measurement. It uses a coil as the detector, and it varies the magnetic field by tuning an electromagnet. However, because the coil is not sensitive to the detection of low-frequency signals, ionization detectors usually require above 10 kHz. For example, most of the ionization detectors from standard work in the range of 10 kHz to tens of megahertz. And on the right is a fast field cycling NMR ionization detection. polarization field of fast field cycling (MR) affect the performance of the OPMs. Thus, it will limit the bandwidth of the use of the device. So we tried a new approach based on mini OPMs with shuttle NMR for ultra-wide range ionization measurement. Next, I will introduce the ultra-wide range shuttle NMR magnetometry. Here shows the device, and we can flexibly choose the realization region of the sample by shuttling. It consists of three magnetic field regions: high field, low field, and zero to ultra low field. The high field is provided by permanent magnet, and the low field is provided by an electromagnet. And the zero to ultra low field is provided by a magnetic shield. And there is a shuttle system driven by a servo motor. It enables the sample to stay in different magnetic field regions and relax. And there is a penetrating flat solenoid providing the magnetic for number precision. Finally, we can detect the FID signal of the samples in zero to ultra low field region. In addition, an OPM array is designed for differential detection, which is used to improve the performance of the device. And this photo shows a system we have built. A y-axis is used as a sensitive axis of detection, and the direction of high field. This is the servo motor used to power the shuttle, and the sample can be shuttled within 105 milliseconds. And this is a OPM array for detection, and there is a pair of Helmholtz coils with two sets of saddle coils on the support structure to provide the pulses. This is an electromagnet to provide the low field, and this is a permanent magnet to provide the high field. It can available up to 2 Tesla. And this is our experiment setup. There are 3 sequences from ionization measurement corresponding to 3 magnetic field regions from 1 Hz to 100 MHz. And the initial position of the sample is always at 0 to ultra low field region. For the sequence of high field, the sample will be shuttled to the high field region, wait for a given time, then returns to 0 and ultra low field region for detection, and a guiding field is applied when transferred. And then a half of pi pulse is applied in x-axis, and then we can get the record of the FID signal. In high field, what we actually measure is the establishment rate of the polarization, and which can be considered equivalent to the longitudinal realization rate, so we can get the recovery curve of T1. For the sequence of low field, the sample needs to fully polarized in high field region first, and then shuttle to low field region to wait and relax. And the electromagnet will provide a Z direction field. At last, the sample is shuttled to 0 to ultra low field region for detection with a pulse of half a pi, and it is consistent with the non-polarized sequence, so we can get the decay curve. For the sequence of 0 to ultra low field, after fully polarized in high field region, the sample is shuttled to a 0 to ultra low field region and wait for time to relax in the field. the field is supplied by the solenoid, and at last a path of half a pi is supplied to x-axis, and we can get a decay curve to fit. And with the 3 sequences, we can measure the T1 of the sample in an ultra-wide range of field. And next, I will show a preliminary result of the experiment. First, we evaluate the device using water as a representative sample. On the left, this is one shot FID signals from 3 channels of OPM array, and on the right is the spectrum of the FIDs. It achieves the signal to a noise ratio of 49.3 for a single channel, and get the and 69 after differentiation, as well as a width of 478 megahertz. And we performed the ultra-wide range shuttle NMR ionization measurement on water at 22 degrees Celsius. A representative result in each region is shown separately. The time and the frequency domains and the corresponding T1 fitting curves are presented for 0 to ultra low field and low field and high field. In line with our expectation, there is a decay curve in 0 to ultra low field and low field, and a recovery curve in high field. And this is the results of the ionization measurement from 1 Hz to 18 megahertz are shown. And they are consistent with commercial FFC fast field cycling MR instruments in the low field region. We have seen that a molecular contrast agent as a sample in order to expand our application in biomedicine. And this contrast agent can be applied to imaging gliomas in the brain. And the blue part of this molecular is the targeting peptide, which can bind with the transferrin receptor, allowing for more efficient transport to the brain for imaging. And the red part is the iron complex contrast agent, which can bind with transferrin. We usually need to determine the ionization properties to measure its effect. So the graph shows the results of the measurement for this contrast agent. Each data point represents the result of 4 averages. And the representative result in each region is shown separately in 0 to ultra low field, and the ionization rate can reach 5.1. And while in high field region, the value is 2.5. We also compared the results with a commercial instrument, showing greater agreement in the low field region. And the difference between our instrument and a commercial instrument may be due to the temperature. And while the commercial fast field cycling equipment sample are at 30 degrees Celsius, and our samples are at room temperature of 22 degrees Celsius. And finally is our outlook section. As a device under development, the ultra-wide range shuttle MR demonstrates the capacity to ionization detection within an ultra-wide ionization field. And the ultra-wide range ionizatometry could extend the traditional exometry to near zero field, and a benefit for evaluation of MRI contrast agents. And because of the capability of the low frequency signal detection, which would render the technique highly applicable in reionization measurement of metal contents, example batteries. And the upper limit of the reionization measurement in our device is related to the speed of the shuttle. And the detection performance needs to be further improved by optimizing the magnetometer array. And okay, for this work, I would like to express my sincere gratitude to my supervisors, Professor Xin Zhou and Professor Qianyue Hu, and thanks all the people involved in this work. Okay, that's all. Thanks for your attention. If you have any questions, please contact us at the following email address. And thank you very much.